Now we start the section 15.3, potential function and independent of paths. Okay. Suppose f is a continuous function, and differentiable, continuous and first differential function, and domain is Rn and range is R. And if there exists a capital function capital F, which is a gradient of F, then the function, the vector field, the vector valued function, Rn to Rn, if there exists a capital F such that del gradient of f is equal to f, then we say little f is a potential function of capital F. And we call this capital F, this vector valued function in vector field, we call this capital F is conservative. It's a conservative of f, the potential function f. Okay, here's the definition of all those explanations. Let f be a vector field. Then f is called conservative vector field if there is a scalar function f such that gradient f is equal to f. And this function little f is called a potential function or a scalar potential for this vector field f. Okay? Conservative. Here is one example. Then if this capital F is the vector valued function xi plus yj, then the little f little f of xy is equal to xy, then first derivative of this f with respect to x is with respect okay. This is one example that if this f should be y and x, then and the little f of xy is xy, then partial derivative of this with respect to x is y, and the partial derivative of this with respect to y is x. So this yx satisfies this condition, which is this gradient f is little f is equal to f. So this if we change y and x in capital F, then this f is a conservative vector field which has a graph like this, y and x. And these will be used later. Okay, here. If m and n has a continuous first order partial derivatives, and the vector field, capital F of xy, which is m of xy I plus n of xy j is conservative, then in simply connected domain, we have my is equal to ny. The partial derivative of m with respect to y is same as partial derivative of n with respect to x. Okay. M with y and n with x. Okay. Okay. Here, this you must not familiar with the simply connected region. Simply connected region. Here, we call this is a simply connected region, and this is not a simply connected region. If we have a hole in the region, then this is not. This is an example of not simply connected region. We have a simply connected. If if we have a dotted line here, then we call it is open simply connected region. If this region does not include the boundary, then we call it is open simply connected region. Okay, here. Okay. But this if it's conservative, we always have this condition. But the converge of this theorem is not true in general. Okay. Here is one example. Let f of xy is capital F of x is like this. It's a vector function on this region. Here, this is r square minus the origin. Origin is not there. It's like this. See, it is a whole region except the origin. So we can write. We can think this region has a hole in it. So it is not simply connected. So okay. In this case, In this case, the partial derivative of m with respect to y, which is this, is y square minus x square over this. And partial derivative of n with respect to x is this. They are same. But gradient of f, this is not conservative. This is an example for which this satisfies, but this is not conservative, because this function was defined is not defined in a simply connected domain. Okay. And one other example, one other comment on it. This is not a simply connected. This is the simply connected region. This is not also simply connected region, if it's divided like this. And these are all the different domains that we can think. Okay. Anyway. Okay. But here is a one theorem that gives us the converse of the theorem too, with more conditions. Here what the difference is. If it is an open simply connected region D, then we can have the converse of the theorem too. Let's see. Let capital F is Mi plus Nj be a vector field on an open simply connected region D. Suppose that M and N has continuous first order partial derivatives, and My is equal to Nx. Then a vector field F is conservative. That's the converse of it. Okay. If this works, then we can do many things. Here's one remark. Suppose f of xyg and is mi, mj, nj plus pk is a vector field on a simply connected domain where m and p has continuous first order partial derivatives. Then f is conservative if and only if the partial derivative of p with respect to y is same as partial derivative of n over partial derivative of n with respect to g, and derivative of p with respect to x is same as derivative of m with respect to g, and derivative of n with respect to x is equal to the partial derivative of m with respect to y. Okay. So this condition expanded to this for the vector values function of 3 variables. Okay. So I showed you a graph of like this. In that case, round x, round y, and round g is written, and m, n, and p is written. Then the partial derivative of this one with respect to the x is same as partial derivative of m with respect to y is same, and partial derivative of p with respect to y is same as partial derivative of m with respect to g, and partial derivative of p with respect to x is same as partial derivative of m with respect to g. I say these are the things that I was trying to say here. This is what it said. Then we can say this vector field is conservative. The reason that we learn this concept is it is very popular in physics application. According to Newton's law of gravitation, then this when f is given like this, f of xyg is little m times mg over square root of x square plus y square plus g square, where capital X is a xyg vector, is a position vector of the object with mass m from one object with mass capital M, and g is a gravitational constant. Then gradient of f, this vector field has has the potential function f as like this. Okay, here. Then, as you see on this, we can, okay. And this satisfies as this is an example of vector field which is conservative and whose position vector is like this. And this equations comes out from the nature in the Newton's law of gravitation. Okay, the one example of conservative vector field. Suppose f is a vector function like this. Then, as you see, this m, n, and p are written like this. And round x, round y, and round z are written like that. Then check. Partial derivative of y square with respect to y is 2y. And think about partial derivative of this with respect to x is what? Is also 2y, isn't it? They are same. Similarly, partial derivative of this with respect to y is 3 times e to the 3g. And partial derivative of this with respect to g is 3 times e to the 3g, isn't it? They are same. And partial derivative of y squared with respect to g is 0. And partial derivative of this with respect to x is 0. They are same. So these three conditions hold. And this is the way to check. This and this same, and this and this same, and this same, like that. Then, so we checked all those three conditions, and we checked it satisfies this. So we can say it is conservative. And this is a potential function of it. Because the gradient of this is this. Okay, here's another example. Determine which of the two vectors fields are conservative. Okay, the first one, here we have m and n, and my and nx, we found it, but they are not same, so it's not conservative. For this one, m is this, 1 plus 3x square y, and n is x cubed minus 2. From here, partial derivative of this with respect to y is 3x squared, and partial derivative of this with respect to x is 3x squared. They are same, so it is conservative. Okay? But for the example 3, partial derivative of here we have m, n, and p, and as you see, py is not same as nx, so they are not satisfying the three conditions that was asked here. It violates this one. So it is not conservative. All those can be checked in here. Okay? Here. So for the function 4x squared minus x cubed, whether check they are same or not. They are different. But I asked them whether they are same or not. They said it's not same, so it's false. So it's not conservative. Okay? For this this vector field in this R3, I checked it. And two of them are same, then one is different. So it said it does not satisfy all three conditions. So it's not same. But what else? 1 and 2. I think 자, 2군. 이게 원래 내가 3개의 example 다 해서 첫 번째 거는 false고 두 번째 거는 true고 세 번째 거 요거 세 번째 거 이제 벡터에서 이게 컨서버티브 아닌 걸 하려고 그랬는데 내가 타입 치다가 세 번째 걸 여기서 지웠나 보다. 두 번째 해놓고 요거 고치도록 하자. 그러면 we can so actually I intended to make the multi-cell that can check the previous example of 3 and first one is not conservative and second one is conservative and third one is not conservative. And those are the code that I made. Okay, so we can check it. Next, independent of path. If f is conservative vector field with potential function pi, then the line integral from A to B is independent of path joining A to B. Okay, so if it is conservative with the potential function pi, then this integral can be written in this way because of the potential function like this, which can be written in this way. And this integral can be found as a pi of b minus pi of a, which means with the, which path we use to do the integration, it does not change the result. So it can easily found by this, which looks like the fundamental theorem of calculus. Okay, there is an useful property of line integral is in conservative field when the path of integration is a closed field curve. If it's a closed curve, then this B point and B and A, those 2 points are same. So these values must be same. So the value should be 0. Okay, so if the vector field is conservative on a domain, and if and only if the integral f dr is equal to 0 around every closed curve in the domain D. Okay, so if it's conservative and if and only if the integral on a closed curve is 0. Okay, so I will explain some more. Yeah, this gives us one more criteria to check whether the given vector field f is conservative or not by just checking an integral on a closed curve in the domain. Okay, the vector field f, except the origin, has a no potential function, although my is equal to ny. It's round f round y is like this, round n over round x is like this. They are same, but it is not. We don't have a potential function, because the origin was not simply connected, and also it's not conservative because there's no potential function. Actually, this is the example that I was trying to show you at the earlier page, the first page. This was it. Suppose that a closed curve is a unit curve. Okay, unit curve is round, it's closed from 0 to 2 pi. Then first we have capital F is like this. Then check round the derivative integral like this. This is what? This is equal to 2 pi. If this function is a conservative, if it's conservative vector field, then it should be it must be a 0. But the integral was not 0 on a closed on a closed curve in the domain. So we can say this vector field is not conservative easily, not by instead of checking all the partial derivatives. Test the existence of potential function for the vector field like this. Okay, so if it's conservative, then we have potential function. So we just check the partial derivative of m with respect to y and partial derivative of n with respect to x. Check it. They are not same, so it's not conservative. Okay? Okay. So there's no potential function. Okay, one thing. Then now next question is for a conservative vector field, how do we find the vector function? This is the next question. 이제 중요하지 않겠어요? 자, 이제 컨서버티브한 거 보이고 하는데 이제 벡터 펑션이 포텐셜 펑션이 존재하냐 안 하냐 이런 문제들을 체크하는 중건 다 보였어. 그럼 이제 F가 벡터 필드가 컨서버티브 하면 그럼 포텐셜 펑션은 뭐냐를 찾는 방법에 대해서 다음 예는 소개하겠다는 거예요. Okay, what is the potential function for the conservative vector field like this? Okay? We check whether it is conservative or not. Here, P and Q are here. It's M and N. Anyway, partial derivative of this one with respect to y and partial derivative of this with respect to x are same. So they are conservative. So there exists the potential function. So let's try to find it out. Okay, we know that f is conservative. So f is conservative. Suppose f is a gradient of f. Then so from here we do the antiderivative. The partial derivative of f with respect to x was like this. So we do the integration. Then we have constant value, and we have like this. Then the partial derivative of f with respect to y was like this. So so this and this should be are same. So this should be same as this, which says k prime of y is equal to minus 2, which means k of y is minus 2y plus c, which means the f of xy is x plus x cube y plus this k of y, which is this. So this is the answer. X plus x cube y minus 2y plus c. So it's just do the integration and check the integral constant to find the entire derivative, which is f of xy. This can be easily done in Sage. Let's define a function. We have a function y, and m is like this, n is like that. Then solution, we solve the differential equation are solved on this one, and then simplify it to have it. And this is the solution that we had, isn't it? Isn't it? Mm-hmm. And this function is conservative. Yeah. Mm-hmm. And this is the value that we have seen in here, which is x cube y minus 2y plus x minus c. Right? Plus c, whatever. Yeah. So this is the answer that you have. And I think this is the last part of it. Yeah, last part of it. Work done by force. Work integral. Okay. Work can be considered. Integral line integral can be considered as a work done. Let me explain it. Let F be a vector field such that Mi is equal to Nx, and let A and B be 2 points of D. And let F be a potential function for this vector field. Then for any piecewise smooth curve C from A to B, and this can be written in this way. Thus, the line integral in this case depends only on the end point A and B, not on the curve C. It's path independent. So, thus we may write this integral in this way. Just this integral like this. So, natural application of the line integral is to define the work done by a force. Work done by force can be written as a line integral like this, but this is can be written in this way, just by FB minus F of A. So we use those facts for the followings. Okay. The work done by a conservative force field in moving a particle from A to B is independent of paths joining A and B, but this depends only on the end points A and B. In such case, a scalar potential pi exists such that force field capital F is gradient of pi, then the work done from A to B equals to just P of B minus P of pi of A. Okay? This is so work can be easily found if we can find the function, the potential function, pi. If C is a closed smooth curve and F is a conservative field, then it's always 0 along any closed curve C. This is what I mentioned earlier. Okay? And that this is a Sage code for the example 5 that gives us a line integral as a 4. This, okay? Okay, this line integral and vector and this line is can be found in here. But let's see. Example 5. F of x is defined in this way. Then there's a 3 paths, well, C1 and C2, C3 to go all the way. So we find the integral of this one on whole this path. Then we do integrate. We do find it on the on three pieces from 3 pieces. We are looking for this one. This can be found in from 0 to from to this and from here to, from the A. This can be written this way. This can be written this way, and this can be. This can be written this way, but and this can be found as this. Okay, this is the way that we do it, but the other way, this integral, we will learn the Green's theorem for the computation of this to find it in the better ways. Okay. This method, I use the Green's theorem to have the answers. Okay. These computations can be simplified if we use the Green's theorem that we will learn later. And now I have shown you the Sage code to solve these problems. And this is examples in section 15.3. And whether to check the conservative or not, and find the potential of f for this function. And this code gives us find whether it's conservative or not. We check this is conservative, and we find the potential function is this code. I expect you just use code to deal with the problems and others. And the next example, and the problem is asking to find the total work done in moving a particle by a force field A along the curve from t is equal 1 to t is equal to t. This can be formulated in this way. Do the integral, and x, y, g. This code are a little different. First part, x of t should be 3x y and 5g and x. Oh, I see. We substituted this. X is t square plus 1, and y is 2t square, and g is t cube, and such. And then we define a function and find the derivatives and define. Oh, so with this setting, we define a of t as a 3x y of t and minus 5z and 10x, and we do the integration of this, which is a of t times dot product, inner product of a of t and d of r, f, and we do integrate f from 1 to 2, and this gives us the answer of 303, which was done in here. We define a function a of t, and we integrate this capital F of t, which gives us the answer, it is 303. And we also can deal with work done, was found by capital F of b minus f of a, which is also gives us, should give us the same answers. Okay. Anyway, yeah, I think that this is the end of section 15.3. Later, we have seen this integral can be written in this way like this. And this theorem is called the Green's theorem. Then instead of we do the integration like this, we can do the integration in this form, which is much easier to integrate. Okay, we will deal with this one in the next class. Okay, any questions? Okay, then class dismissed.